now, as we live in this modern world, invisible signals are passing above your head. They guide ships in the oceans, planes in the sky, farmers and fields, and even the time on your phone.
This is all GNSS.
GNSS satellite, connectivity to your future.
And today, we'll show you how it works and why it's one of the most important technologies in our world.
Up there in space, constellations of satellites orbits the Earth in perfect synchronization. Each one carries an atomic clock that sends precisely timed signals back to us.
GNSS is just knowing where you are. It's about keeping the whole world moving in sync. It began in 1957 when the Soviet Union launched the first satellite called Sputnik 1. The scientists observed the Doppler effect when the pitch of the signal changed as the Sputnik moved. This discovery demonstrated that an object's position could be determined based on frequency shift of a known signal.
From that discovery, navigation by satellite was born. In the 1960s, the US Navy built the transit system. It guided ships, but it only worked when satellites were overhead.
The world needed something better, faster, more accurate, and always available.
That's when new programs began shaping the future of navigation.
One of these was the Timation program by the U.S. Naval Research Laboratory. Launched in 1967, Timation satellites proved that using highly accurate atomic clocks in space could make precise timing and therefore precise positioning possible.
At the same time, the U.S. Air Force was developing the 621B program, which introduced the idea of using Code Division Multiple Access or CDMA to allow satellites and receivers to communicate more efficiently. These breakthroughs paved the way for what would become the Global Positioning System or GPS, the first fully operational global navigation satellite systems.
In 1973, the U.S. Department of Defense created GPS, the Global Positioning System. Led by Colonel Bradford Parkinson, GPS launched 24 satellites into orbit.
The first experimental satellite, Navster-1, was launched in 1978, marking the start of GPS testing and demonstration. Over the next decade, more satellites were launched, and by the early 1990s, GPS reached what's known as initial operational capability.
By 1995, GPS became fully operational. At first, civilian signals were less accurate, but the year 2000, that restriction was removed, and suddenly, GPS became a part of everyday life.
While GPS was the first fully GNSS, other nations soon developed their own systems.
Japan built GLONASS. Europe built Galileo, and China launched Baidu.
GLONASS or Globalnaya Navigationaya Sputnikovaya Sistema. It began in the 1980s and reached full operation in 1996. After a decline in the 1990s, Russia restored and modernized it in the 2000s. And today, it's a key global navigation system.
Europe followed with Galileo, created by the European Union and the European Space Agency in the early 2000s. It's unique because it's civilian-controlled, providing high-precision services. Galileo started offering initial services in 2016 and is expected to reach full operational capability by the mid-2020s. China launched Baidu, which began as a regional system in 2000 and expected to full global coverage by 2020. Baidu stands out for its advanced two-way communication and regional augmentation capabilities.
India created NavIC, and Japan designed QZSS for accuracy in cities and mountains.
NavIC or Navigation with Indian Constellation. It focuses on providing accurate regional coverage over India and nearby regions, serving both civilian and strategic purposes. And Japan designed QZSS or Quasi-Zenith Satellite System to improve accuracy in cities and mountainous areas. It ensures satellites stay visible even when tall buildings or terrain block signals.
Today, all this system makes up GNSS, multiple constellations working side by side.
Each satellite is like a giant clock in space. It sends signals with its exact time and position.
A GNSS receiver in your phone, in your car, or an airplane listens to at least 4 satellites.
Imagine if one satellite signal says you're here, another says you're there. The receiver compares the time it took for each signals to arrive. Even a billionth of a second difference can shift your position by meters.
That's why timing accuracy is super important. GNSS satellites use atomic clocks to keep perfect time, so your phone can pinpoint your exact spot on Earth, whether you're walking, flying, or sailing.
The trilateration process calculates distance. It measures how long it takes for signals to arrive. Where sphere overlap, it finds your location.
On Earth, ground stations keep satellites in check, correcting their orbits and synchronizing their clocks. It's constant dance between space, Earth, and your device.
GNSS signals travels in L-band of radio waves. Different systems use different frequencies. GPS is L1, L2, and L5. Galileo has E1 and E5, while BeiDou has B1, B2, and B3. The effectiveness of these signals depends on how they are modulated and transmitted. Modulation is how information is placed onto a radio wave. It's what lets satellites send data without overlapping each other.
Modern systems like Galileo and the new GPS signals use binary offset carrier or BOC modulation. This shifts the signal slightly, giving better accuracy and resistance to interference. Perfect for precise navigation.
And each GNSS has its own set of frequency bands with the L band between 1 and 2 GHz. These frequencies help the signals travel through clouds and the atmosphere with minimal delay.
These signals use advanced modulation like BPSK and BOC, making them resistant to interference. And by using multiple frequencies, receivers can correct errors caused by the atmosphere.
GNSS is everywhere. In transportation, it guides planes, ships, and cars.
From aviation to public transport, GNSS improves efficiency and safety. Airlines rely on it for precision approaches. Ships use it to navigate harbors, and even buses and taxis depend on it for route optimization.
In surveying, it measures land with centimeter precision.
Engineers and geodesists use GNSS for cadastral mapping, civil works, and tectonic monitoring. Thanks to real-time kinematic positioning, surveyors can now map large areas with accuracy down to the centimeter, revolutionizing construction and urban planning.
In agriculture, farmers use it to plant seeds and harvest with accuracy.
It's called precision agriculture. Using GNSS helps farmers reduce waste, save fuel, and increase crop yield. It even helps in monitoring soil conditions and tracking environmental changes for sustainable farming.
In science, it helps monitor earthquakes, lasers, and even space weather. Researchers also use GNSS to study the atmosphere, measure ocean levels, and observe the movement of ice sheets. Space missions depend on GNSS to guide satellites, synchronize instruments, and collect accurate data for scientific discovery.
And in finance and power systems, GNSS keeps clocks synchronized down to nanosecond, essential for banks and electricity grids.
Without GNSS timing, financial transactions, internet data transfers, and even phone networks would lose synchronization. It's a silent backbone of modern life, ensuring that every second counts.
From navigation to science, from agriculture to finance, GNSS connects our world with precision, reliability, and innovation. What began as a military system has become an essential part of our everyday life.
But GNSS isn't perfect. The signals are extremely weak, weaker than the light bulb seen from space.
These weak signals can easily be disrupted. Even unintentional interference from radio or communication devices can interrupt GNSS reception, while deliberate jamming can block signals entirely, a serious problem for navigation and safety operations.
They can be blocked by jamming or tricked by spoofing.
Spoofing happens when counterfeit signals mislead receivers, giving false positions or times. That's why encrypted services like Galileo's PRS or the military's GPS Y code exist to protect sensitive systems. But civilian users are still at risk of these threats.
And tall buildings create multipath reflections, confusing receivers in what we call urban tangents.
When signals bounce off walls or terrain, the receiver gets delayed or distorted data, reducing accuracy. The atmosphere adds to the problem. The ionosphere and troposphere can bend or slow signals depending on temperature, pressure, and humidity.
Even though GNSS covers the whole planet, it still depends on massive infrastructure like satellites, ground stations, and receiver networks. If any parts fails or gets attacked, it can cause service outages. That's why scientists are developing backup systems and hybrid navigation using inertial sensors and terrestrial signals.
And sometimes, GNSS just can't reach us at all. Inside buildings, dense forests, underwater, or in deep urban canyons, signals get blocked completely. To fix that, engineers combine GNSS with local positioning or Wi-Fi based navigation.
The future of GNSS is multi-constellation, multi-frequency receivers that combine all signals for centimeter accuracy. Global systems are being upgraded with stronger, more robust signals that resist interference and improve coverage, even in dense cities or mountainous areas. This modernization ensures that GNSS remains reliable and accessible everywhere.
It will integrate with 5G networks, drones, and autonomous vehicles.
Future GNSS will work hand in hand with new technologies, the Internet of Things, self-driving systems, and even smart cities, with sensor fusion from LiDAR, cameras, and inertial navigation. These systems will navigate and make decisions with incredible precision.
Security and resilience are also part of the future. Researchers are developing encrypted and authenticated signals and even backup systems using low Earth orbit satellites, all designed to prevent jamming or spoofing. These innovations will protect critical infrastructures like aviation, banking, and power grids that rely on precise GNSS timing.
High-precision GNSS will change industries too, from agriculture to climate research. With centimeter-level accuracy, farmers can plant efficiently, science can monitor earthquakes, and engineers can design smarter cities.
And beyond Earth, GNSS will guide missions in orbit, on the Moon, and one day, even on Mars.
NASA and international space agencies are already adopting GNSS for deep space navigation, turning what once guided cars and ships into a universal system for the solar system. The evolution of GNSS continues, from global navigation to universal synchronization. Modernized, resilient, and deeply integrated with future technologies, GNSS will remain one of humanity's most vital tools, guiding us not only across the Earth but far beyond it.
From Sputnik's first beep in 1957 to guiding billions of smartphones today,
GNSS has become an invisible thread connecting all humanity.
This is a story of science, innovation, and international cooperation.
And it will continue to shape our future on Earth and beyond.
This is GNSS, the silent force that guides our world.